Recently, a group of astronomers verified the Einstein's general theory of relativity by detecting the light, or rather more precisely, X-rays from behind a black hole named as I Zwicky 1 for the very first time. So first of all, what do we understand by a black hole? For that, we have to understand about the death of the star. And for that, we have to go back to the story of star formation. A star is basically formed from the cloud known as nebulae, which consists of dust and gases at very high temperature. Due to different densities of materials, the gravity collapses the nebula into a spherical giant. Then hydrogen gas fuse themselves into deuterium and then to helium gas by proton-proton cycle. Helium gas is also initially present as a starter, which increases the production of more helium gas and hence more fuel. Soon, gravitational force and fusion settle peace, and there you have a star. But fuel has to end someday, isn't it? So when the fuel is about to end, the star starts to collapse under its own gravitational force. But it soon reaches a point where electrostatic repulsion came in effect and opposes gravitational force. But soon the gravity dominates, and then the star again collapses and explodes into a gigantic explosion called a supernova, which releases energy higher than the sun will release in its whole life. After that, there is only the inner core left, and this is called the death of the star. There are three death products of the star: white dwarf, neutron star, and black hole. Now, black holes can only be formed by the death of a massive star. It was John A. Wheeler who coined the term black hole in 1967. Even on 10th of April 2019, astronomers from Event Horizon Telescope project released first ever image of a black hole. Supermassive black holes are generally 1,000 times more massive than our sun, but smaller than the radius of our sun. The radius of black hole's event horizon is what we call as Schwarzschild radius. Its formula is gm by c square, where g is the universal gravitational constant, m is the mass of the black hole, and c is the speed of the light. It means that if you compress any material to this radius, it will become a black hole. But it is just theoretically measured. Practically, sun can't be compressed that much, as there is not much fuel for it to become a black hole, even a neutron star. Anyways, we should focus on black hole now. Now, black hole has several circular layers or regions called as accretion disk. It doesn't happen that any material, even the light, is just directly sucked into the black hole, but it first orbits the black hole with very high kinetic energy. That kinetic energy, however, due to friction, converts to heat energy. As soon as the particle loses energy and angular momentum, it spirally enters the black hole. High energy particles start to radiate the energy of X-ray spectrum, and due to the collision of these high energy particles, there forms a hot structure which resembles that of a lamp post. This hot structure is called as corona. This corona consists of high energy X-rays. Physicists are still unsure about how corona is actually formed, but okay, never mind. Well, this hot corona ejects X-rays which hit the accretion disk and then reflects off from the accretion disk to us. Now, X-rays are being detected from front side by various X-ray telescopes, but in January 2020, X-ray detectors, a new star and XMM Newton, detected something more than just front X-rays. They detected both blue shifted and red shifted emissions from various regions of the accretion disk. Blue shifted emissions are detected from the front or approaching side of the disk, while the red shifts are detected from receding or back side of the disk. There is a significant difference between the wavelengths of front and back side light rays due to Doppler and gravitational redshift. Due to that, the difference in energy of photons arises due to gravitational redshift, which bends the light on basis of how close it gets to the event horizon. So we can find the distance between those 2 points of front and back side by detecting the time difference between those two light rays to reach to us. This isn't like gravitational lensing where we see the apparent position of any star or any material. But here we detect the light ray from behind a black hole, which is traveling via the curved space-time to reach us and stunning us with this huge discovery.